Welcome to our first lecture on a fascinating class of organic compounds, the alkyl halides. We defined an alkyl halide as a molecule where one or more halogen atoms are directly bonded to an sp3 hybridized carbon atom of an alkyl group. You might be surprised by how common these compounds are in everyday applications. For instance, chloroform, or CHCl3, is a well-known organic solvent. Then we have Freon 12, a chlorofluorocarbon historically used as a refrigerant, and halothane, which is a widely used medical anesthetic. Because halogen atoms are significantly more electronegative than carbon atoms, the bond between them, often written as C-X, is highly polarized. This electronegativity difference pulls electron density towards the halogen, creating a partial negative charge on the halogen and leaving a partial positive charge on the carbon atom. Let's look at the trends across the halogens. As we move down the periodic table from fluorine to iodine, electronegativity decreases, but the atomic radius increases, making the carbon-halogen bond longer. Interestingly, the bond dipole moment is highest for the carbon-chlorine bond, not the carbon-fluorine bond, because the overall dipole moment depends on both the charge separation and the bond length. We can quantify this polarity using the dipole moment equation, where mu equals 4.8 times delta times d. Here, delta represents the amount of charge separation, and d is the bond length. This inherent polarity is exactly what makes alkyl halides such incredibly useful chemical reagents. The reactivity is dominated by this dipole, which typically leads to the carbon-halogen bond being broken during a reaction. When naming these molecules, IUPAC rules treat them simply as alkanes with a halogen substituent, using prefixes like fluoro, chloro, bromo, or iodo. However, you will frequently encounter common names for specific structural patterns. For example, molecules with one carbon and two halogens are called methylene halides, those with three halogens are haloforms, and those with four are carbon tetrahalides. We also classify alkyl halides based on their substitution pattern. Depending on how many other carbons are attached to the carbon bearing the halogen, they can be primary, secondary, or tertiary. Furthermore, if a molecule has two halogens, we use specific terms. A geminal dihalide has both halogens on the exact same carbon, while a vicinal dihalide has them on adjacent, neighboring carbons. Now, how do we actually make alkyl halides? One straightforward but often messy method is free radical halogenation of an alkane. The problem here is that it usually produces a complex mixture of mono, di, and trihalogenated products. Because it is hard to stop the reaction at just one substitution, it is generally considered an inefficient synthetic route, unless you have specific conditions to control the selectivity. A much more targeted preparation method is allylic bromination. The term allylic refers to the position immediately adjacent to a carbon-carbon double bond. If we take cyclohexene and react it with bromine in the presence of light, we can selectively substitute an allylic hydrogen for a bromine atom, yielding 3-bromocyclohexene in a very respectable 80% yield. The reason this reaction works so well is due to the stability of the intermediate. A bromine radical abstracts the allylitic hydrogen, leaving behind an unpaired electron on the carbon. This creates an allylitic radical, which is highly stabilized by resonance with the adjacent double bond. This stable radical then easily reacts with another bromine molecule to form our final product and propagate the radical chain. In the laboratory, instead of using hazardous bromine gas directly, chemists frequently use N-bromosuccinimide, or NBS, for these allylic brominations. NBS is fantastic because it reacts with trace amounts of HBr in the flask to slowly and continuously generate very low concentrations of molecular bromine, which keeps the radical chain reaction running smoothly without unwanted side reactions. Beyond radical reactions, there are several other excellent ways to synthesize alkyl halides. We can make them from alkenes and alkynes through addition reactions, from alcohols via substitution, or even from other alkyl halides using halogen exchange. We will dive into the specific mechanisms for these transformations in later chapters. Because of that polarized carbon-halogen bond we discussed earlier, alkyl halides are incredibly versatile in their reactions. The halogen can easily leave, taking its bonding electrons with it to form a stable halide ion, making it what we call a good leaving group. This opens the door for two main pathways: substitution, where a new atom replaces the halogen, or elimination, where the halogen and a neighboring hydrogen are both lost to form a double bond. In practice, substitution and elimination reactions are almost always in direct competition with one another in the reaction flask. The pathway that wins depends heavily on the structure of the alkyl halide, the reagents we choose, and the temperature. Understanding how to control this competition is key, which leads us directly into our detailed look at the mechanics of nucleophilic substitution. Continuing our look at alkyl halide reactivity, we see that these compounds generally undergo two main types of reactions: nucleophilic substitution and elimination. In a substitution reaction, a nucleophile uses its lone pair to attack the carbon and displace the leaving group. Alternatively, in an elimination reaction, specifically dehydrohalogenation, a base abstracts a proton from the alkyl halide, which leads to the formation of a new pi bond as the leaving group exits. Because most nucleophiles can also act as bases, these two pathways often compete. The preference for one over the other depends heavily on the specific reaction conditions and the structure of the alkyl halide. Let's focus on a specific type of substitution, the SN2 reaction. SN2 stands for substitution nucleophilic bimolecular. Consider the reaction between a hydroxide ion and methyl iodide to form methanol. The hydroxide ion is an excellent nucleophile because its oxygen atom carries a full negative charge and unshared electron pairs. The carbon atom in methyl iodide is electrophilic. Why? Because it is bonded to a more electronegative halogen, iodine, which pulls electron density away, leaving the carbon with a partial positive charge. Electrostatic attraction draws the nucleophile to this electrophilic carbon. The defining feature of the SN2 mechanism is that it is concerted. This means the reaction takes place in a single, continuous step. As the nucleophile donates its 2 electrons to attack the carbon, the bond to the leaving group must simultaneously break. This is because carbon can only accommodate a maximum of 8 valence electrons. The transition state, shown in the brackets, represents the exact moment where the new carbon-oxygen bond is half formed and the old carbon-iodine bond is half broken. If we map this concerted process on an energy diagram, we see a single smooth curve. The reactants start at a certain energy level and must overcome an activation energy barrier to react. The peak of this barrier is the transition state. It is crucial to understand that the transition state is a fleeting point of maximum energy, not a stable intermediate that can be isolated. Once the system passes through this high-energy arrangement, it quickly relaxes down into the more stable products. The term bimolecular in SN2 comes directly from the reaction's kinetics. Experimental data shows that if we double the concentration of methyl iodide, the reaction rate doubles. If we double the concentration of hydroxide, the rate also doubles. This means the rate law is first order with respect to both the substrate and the nucleophile, making it second order overall. This perfectly matches our concerted mechanism. The rate-determining step requires a physical collision between these two specific molecules. The SN2 mechanism is incredibly versatile and serves as a fundamental tool in organic synthesis. By simply changing the nucleophile, we can transform an alkyl halide into a wide variety of different functional groups. For example, using hydroxide yields an alcohol, using an alkoxide yields an ether, and using a cyanide ion yields a nitrile. We can even use halogen exchange reactions to swap one halogen for another, which is particularly useful for synthesizing fluoro or iodo compounds where direct halogenation isn't practical. Because the nucleophile is actively involved in the rate-determining step, the strength of the nucleophile drastically affects the speed of an SN2 reaction. A stronger nucleophile will react much faster. A general rule is that a negatively charged species is a significantly better nucleophile than its neutral counterpart. For instance, methoxide, which carries a full negative charge, reacts with methyl iodide about 1,000,000 times faster than neutral methanol. We can explain this massive difference in reaction rates by looking at the transition states. When the negatively charged methoxide attacks, the transition state shares that single negative charge between the incoming oxygen and the departing iodine. Both are electronegative, so this is relatively stable, resulting in a lower activation energy. However, when neutral methanol attacks, the transition state forces a charge separation. The oxygen develops a partial positive charge, while the iodine becomes partially negative. This high-energy state creates a much larger activation barrier. At this point, we need to clearly distinguish between basicity and nucleophilicity, as they are related but distinct concepts. Basicity is a thermodynamic property. It is defined by the equilibrium constant for a species abstracting proton. Nucleophilicity, on the other hand, is a kinetic property. It is defined strictly by how fast a species attacks an electrophilic carbon atom. While strong bases are often good nucleophiles, the two properties don't always perfectly align. There are 3 main trends to predict nucleophilicity. First, as we just discussed, a base is always a stronger nucleophile than its conjugate acid, so hydroxide is stronger than water. Second, nucleophilicity decreases as you move from left to right across a row of the periodic table. For example, the amide ion is a better nucleophile than hydroxide, which is better than fluoride. This happens because more electronegative elements hold on to their non-bonding electrons much more tightly, making them less willing to donate those electrons to form a new bond with carbon. The third trend is that nucleophilicity increases as you move down a column of the periodic table. Iodide is a much better nucleophile than fluoride. This is due to size and polarizability. Fluoride is small and hard. Its electrons are held very close to the nucleus, requiring it to get extremely close to the carbon before orbital overlap can occur. Iodide is large and soft. Its outer electrons are far from the nucleus and loosely held. This highly polarizable electron cloud can easily distort and begin overlapping with the carbon atom from a much greater distance, stabilizing the transition state. The solvent you choose also plays a massive role. Polar protic solvents, like water or alcohols, have acidic protons that can form strong hydrogen bonds. If you put a small, hard anion, like fluoride, into a protic solvent, the solvent molecules swarm it, forming a tight cage of hydrogen bonds. The nucleophile is so well solvated that its ability to attack a carbon is severely reduced. To fix this, SN2 reactions often use polar aprotic solvents. These solvents dissolve the polar reactants, but lack the OH or H ions needed to cage the anions, leaving the nucleophile free to attack. Beyond electronic trends, we must consider steric effects, the physical size and bulk of the molecules. Because nucleophilicity requires the molecule to physically approach and attack a crowded carbon center, bulky groups severely hinder this process. Take tert butoxide versus ethoxide. Tert butoxide is a stronger base, but its 3 bulky methyl groups make it very difficult for the oxygen to reach an electrophilic carbon. Therefore, despite its basicity, tert butoxide is a much weaker nucleophile than the streamlined, unhindered ethoxide ion. Now let's look at the other half of the equation, the leaving group. A good leaving group must do a few things. First, it needs to be electron withdrawing to polarize the bond and make the carbon an attractive target for the nucleophile. Second, and most importantly, it must be highly stable once it leaves with the electron pair. This generally means good leaving groups are weak bases, the conjugate bases of strong acids. Halides like chloride, bromide, and iodide are excellent, as are resonance-stabilized ions like sulfonates. Neutral molecules like water or alcohols can also be great leaving groups. What if we have a poor leading group, like a hydroxide ion on an alcohol? Hydroxide is a strong base, so it strongly resists leaving. If we simply mix bromide with methanol, no substitution occurs, but we can use chemistry to our advantage. By running the reaction in an acidic medium, the alcohol oxygen picks up a proton. This transforms the leaving group from a hydroxide ion into a neutral water molecule. Water is incredibly stable on its own, making it an excellent leaving group, and the SN2 reaction can now proceed smoothly. Just as a bulky nucleophile struggles to attack, a bulky substrate is difficult to attack. For an SN2 reaction to occur, the nucleophile must approach the carbon from the side exactly opposite the leaving group. If the carbon is surrounded by small hydrogen atoms, like in a methyl or primary halide, this backside attack is easy. Adding alkyl groups increases steric hindrance. A secondary halide is slower but possible. However, a tertiary halide with 3 bulky alkyl groups completely blocks the backside trajectory. SN2 reactions simply do not occur on tertiary substrates. Because the leaving group physically blocks the front, the nucleophile has no choice but to attack the small back lobe of the carbon's sp3 orbital. This mandatory backside attack has profound stereochemical consequences. As the nucleophile pushes in and the leaving group departs, the other 3 bonds to the carbon are forced to flip inside out, much like an umbrella caught in a strong wind. This results in a complete inversion of stereochemistry. If you start with an s-chiral center, an SN2 reaction will stereospecifically yield the R product. So we've established that tertiary alkyl halides, like tert-butyl bromide, are completely inert to SN2 reactions due to steric hindrance. Yet, if we place tert-butyl bromide in ethanol, a substitution reaction still occurs, yielding an ether. Since it cannot be happening via the concerted SN2 pathway, there must be an entirely different mechanism at play. This alternative pathway is known as the SN1 reaction, or substitution nucleophilic unimolecular, which we will explore next. Moving right along to our next major reaction type, let's examine first-order nucleophilic substitution, commonly known as SN1. Consider the reaction of T-butyl bromide with methanol to form T-butyl methyl ether and hydrogen bromide. When we study the kinetics of this specific reaction, we find something interesting. The rate depends entirely on the concentration of the alkyl halide, T-butyl bromide. The concentration of the methanol nucleophile doesn't affect the rate at all. This gives us a rate law of rate equals K times the concentration of T-butyl bromide. Because the rate depends on only one reactant, it is first order overall or unimolecular. This kinetic data tells us a crucial piece of information about the mechanism. The nucleophile cannot be involved in the rate determining step. It must enter the reaction after the slow step has already happened. Since the nucleophile isn't in the rate determining step, the SN1 reaction must be a multi-step process. Let's look at the mechanism. The first step is the spontaneous ionization of the alkyl halide. The carbon-halogen bond breaks heterolytically, with the leaving group, bromide in this case, taking both electrons. This generates a carbocation intermediate and a bromide anion. Breaking a bond requires a significant input of energy, making this a highly endothermic and very slow process. Therefore, this ionization is the rate-determining step of the entire reaction, which perfectly explains why our rate law only depends on the concentration of the starting alkyl halide. Once that highly reactive carbocation is formed, the subsequent steps happen very rapidly. In step 2, the nucleophile, which is methanol here, uses a lone pair of electrons on its oxygen to attack the positively charged carbon, forming a new carbon-oxygen bond. Because our nucleophile was neutral, the resulting intermediate carries a positive charge on the oxygen. To get to our final neutral ether product, we have a final fast acid-base step. Another molecule of the methanol solvent acts as a base, removing the extra proton from our intermediate. This quick deprotonation yields the final product. We can clearly visualize the fundamental difference between these two substitution mechanisms by looking at their energy profiles. On the right, remember the SN2 reaction, it's a concerted one-step process with a single transition state, where bond breaking and bond making happen simultaneously. But look at the SN1 diagram on the left. It has two distinct transition states separated by an energy valley. That valley represents the carbocation intermediate. The first peak is much higher than the second, confirming that the initial ionization to form the carbocation requires the most activation energy and is indeed the rate-determining step. Because the rate-determining step involves forming a carbocation, the Hammond postulate tells us that the transition state for this endothermic process closely resembles the carbocation intermediate itself. Consequently, anything that stabilizes the carbocation will lower the activation energy and speed up the SN1 reaction. Alkyl groups are excellent at stabilizing carbocations through two mechanisms. First, the inductive effect, where the electron-rich alkyl groups push electron density toward the electron-deficient positive carbon. Second, hyperconjugation, where the electrons in adjacent aligned carbon-hydrogen sigma bonds partially overlap with the empty p orbital of the carbocation. Because of these stabilizing effects, SN1 reactivity follows carbocation stability. Tertiary halides are the fastest, followed by secondary. Primary and methyl halides are so unstable, they generally do not undergo SN1 reactions at all. Notice this is the exact opposite trend of SN2 reactivity. Beyond inductive effects and hyperconjugation, resonance plays a massive role in stabilizing carbocations. If a carbocation can delocalize its positive charge across multiple atoms through resonance, it becomes significantly more stable. A classic example is allyl bromide. Even though it is technically a primary halide, it is highly reactive in SN1 reactions. When the bromide leaves, the resulting positive charge is adjacent to a pi bond. This allows the pi electrons to shift, delocalizing the positive charge over two different carbon atoms. This resonance stabilization makes the formation of the carbocation much easier, allowing the SN1 reaction to proceed rapidly. Just like in SN2 reactions, the quality of the leaving group is absolutely essential for SN1. In the rate-determining step, the bond to the leaving group is breaking. As this happens, the leaving group begins to take on a partial negative charge in the transition state. A highly polarizable leaving group, such as iodine or bromine, helps stabilize this transition state through partial bonding as it departs. Furthermore, a good leaving group must be stable once it is fully detached with the bonding electrons, meaning it should be a weak base. So excellent leaving groups accelerate both SN1 and SN2 pathways. The solvent environment is another major factor. Because the rate-determining step of an SN1 reaction involves taking a neutral molecule and ripping it apart to form two oppositely charged ions, polar solvents are required to stabilize those developing charges. Protic solvents like water and alcohols are especially effective because they can stabilize the carbocation with their lone pairs, and uniquely, they can hydrogen bond to the anionic leaving group, stabilizing it as it departs. We measure a solvent's polarity using its dielectric constant, epsilon. As you can see in the table, as the dielectric constant increases from nonpolar hexane up to highly polar water, the relative rate of the SN1 reaction skyrockets by factors of thousands. Now let's consider stereochemistry. Recall that SN2 reactions are strictly stereospecific, resulting in complete inversion of configuration. The SN1 reaction is not stereospecific. When the leaving group departs, it leaves behind a carbocation that is sp2 hybridized and completely planar. This means the nucleophile can attack the empty t orbital from either the top face or the bottom face. If it attacks from the same side the leaving group was originally on, we get retention of configuration. If it attacks from the opposite side, we get inversion. A mixture of both is called racemization. However, in practice, complete 50-50 racemization is rare. The departing leaving group often lingers nearby as an ion pair, partially blocking the front face, which typically results in a major product of inversion and a minor product of retention. One of the most fascinating complications of SN1 reactions is the possibility of carbocation rearrangements. Because carbocations are highly reactive intermediates, they will often spontaneously rearrange if they can form a more stable ion. For example, if we react 2-bromo-3-methylbutane with ethanol, we don't just get the expected substitution product. We actually get a mixture of structural isomers, the expected product and a rearranged product where the nucleophile attached to a completely different carbon. Both of these products arise from the same initial secondary carbocation formed in step 1. Let's look at how that secondary cation transforms. To understand the rearranged product, we need to look at a process called a hydride shift. In our secondary carbocation, the adjacent carbon is tertiary and has a hydrogen atom attached. To achieve a lower energy state, that hydrogen atom can migrate over to the positively charged carbon. Crucially, the hydrogen moves with its 2 bonding electrons. It moves as a hydride ion. This 1-2 hydride shift fills the empty orbital on the secondary carbon, but leaves a new empty orbital on the tertiary carbon. We have successfully converted a less stable secondary carbocation into a much more stable tertiary carbocation. The nucleophile can now attack this new tertiary center, giving us our rearranged product. Rearrangements aren't limited to hydrogen atoms. If a hydrogen isn't available to create a more stable cation, an entire alkyl group can migrate. Take neopentyl bromide. Ionizing the bromide would create a primary carbocation, which is so unstable it simply won't form. Instead, as the leaving group begins to depart, an entire methyl group from the adjacent quaternary carbon migrates over, taking its bonding electrons with it. This methyl shift bypasses the primary carbocation entirely, directly forming a stable tertiary carbocation. Remember, these rearrangements only occur when a more stable cation can be produced, and they are exclusive to reactions with carbocation intermediates, like SN1. You will never see a rearrangement in an SN2 reaction. Let's summarize the key differences between SN1 and SN2 reactions, as predicting which pathway a molecule will take is a critical skill. For SN1, nucleophile strength doesn't matter since it's not in the rate-determining step, but SN2 requires a strong nucleophile. Substrate reactivity is completely inverted. SN1 favors bulky tertiary carbons to stabilize the carbocation, while SN2 favors unhindered methyl and primary carbons. SN1 requires highly polar ionizing solvents, whereas SN2 often prefers polar aprotic solvents. Kinetically, SN1 is first order, depending only on the alkyl halide, while SN2 is second order, depending on both reactants. Stereochemically, SN1 gives a racemic mixture, while SM2 gives complete inversion. Finally, SN1 reactions are prone to carbocation rearrangements, which are impossible in the concerted SN2 mechanism. Substitution reactions, whether SN1 or SN2, rarely happen in isolation. They are almost always in competition with another major class of reactions called eliminations. In an elimination reaction, instead of a nucleophile replacing a leaving group, 2 atoms or groups are entirely lost from adjacent carbons on the molecule. The electrons that previously bonded those groups are left behind to form a new pi bond, typically generating an alkene. For instance, an alkyl halide can lose both the halogen and a neighboring hydrogen atom as HBr. Just like substitutions, eliminations have different mechanistic pathways. If the leaving group departs first to form a carbocation, and then a base removes a proton to form the double bond, we call this a first-order elimination, or E1, which we will dive into next. Let's turn our attention to elimination reactions, starting with the E1 pathway. E1 stands for elimination unimolecular. Just like the SN1 reaction, the rate-determining step involves only one molecule, the alkyl halide. The reaction begins with a slow ionization to generate a carbocation intermediate. Once the carbocation is formed, the second step is a fast removal of a neighboring proton by a weak base, often the solvent. The electrons that were used for the carbon-hydrogen bond are left behind and go on to form the new carbon-carbon pi bond. Looking closely at the individual steps, step 1 is the slow, rate-determining carbocation formation. The leaving group departs, taking its electrons and leaving a positive charge on the carbon. In step 2, a base comes in and removes a proton from an adjacent carbon. This step is fast. The electrons from that broken carbon-hydrogen bond swing down to satisfy the carbocation's empty p orbital, creating the double bond of the alkene product. Because E1 and SN1 reactions both proceed through the exact same carbocation intermediate, they almost always compete with each other. When the carbocation is formed, the solvent can either act as a base and remove a proton to give the E1 elimination product, or it can act as a nucleophile and attack the carbocation to give the SN1 substitution product. For example, reacting tert-butyl bromide with ethanol yields a mixture of an alkene, 2-methylpropene, and an ether, ethyl tert-butyl ether. The energy diagram for an E1 reaction clearly shows why it is unimolecular. The first step has a large endothermic activation energy. This is the rate-determining transition state where the leaving group departs. The intermediate carbocation sits in the valley. The second step is a fast exothermic removal of a proton with a much lower activation energy. Because the base does not get involved until after the rate-determining step, its concentration does not affect the overall rate of the reaction, and it does not appear in the rate equation. Whenever a reaction forms a carbocation, you have to consider all its possible fates. A carbocation can react in 4 different ways. First, it can simply recombine with the leaving group, taking you right back to the starting material. Second, it can react with a nucleophile to give an SN1 substitution product. Third, it can lose an adjacent proton to a base, giving an E1 elimination product. And fourth, if it can become more stable by doing so, it will rearrange via a hydride or alkyl shift before undergoing substitution or elimination. Now let's look at the alternative, the E2 reaction, which stands for elimination by molecular. This generally occurs when a strong base is present. The strong base is aggressive enough to remove a proton much quicker than the substrate can ionize on its own. Because of this, the reaction takes place in one concerted step. The carbon-hydrogen and carbon-halogen bonds break at the exact same time as the base hydrogen and carbon-carbon pi bonds form. The rate depends on both the substrate and the base, giving a second-order rate equation. In the E2 transition state, we can see this concerted process in action. The base is acting as a base, not a nucleophile, by attacking a peripheral proton. As the base culls the proton away, the electrons from the carbon-hydrogen bond begin to fold in to form the pi bond. Simultaneously, the leaving group is being pushed out, taking its electrons with it. There is no carbocation intermediate here. The partial formation of the new bonds in the transition state helps lower the activation energy. When an alkyl halide has more than one type of adjacent hydrogen, elimination can produce a mixture of different alkenes. To predict the major product, we use the Zaitsev or Zaitsev rule. This rule states that the major product of an elimination will be the alkene with the most highly substituted double bond. This is because more substituted alkenes are thermodynamically more stable. For example, eliminating HBr from 2-bromobutane yields 81% of the disubstituted but2-ene and only 19% of the monosubstituted but1-ene. Because the E2 reaction is concerted, it requires a specific geometry. The orbitals involved in bond breaking and forming must overlap perfectly so electrons can flow smoothly. This requires the hydrogen and the leaving group to be in a coplanar arrangement. There are 2 ways to achieve this: anti-coplanar, where the hydrogen and leaving group are 180 degrees apart, and syn-coplanar, where they are 0 degrees apart. The anti-coplanar conformation is staggered and lower in energy, making it the highly preferred pathway. Looking at the orbital overlap explains why anti-coplanar is preferred. The partial pi bond in the transition state requires the parallel alignment of 2 p orbitals. In the anti-coplanar conformation, the incoming base and the departing leaving group are on opposite sides of the molecule. They are well separated, which minimizes steric hindrance and electron repulsion. In contrast, a syn-coplanar transition state forces the electron-rich base to approach very close to the electron-rich leaving group, creating severe repulsion that makes it energetically unfavorable. Because the E2 mechanism strongly prefers the anti-coplanar geometry, it is a stereospecific reaction. This means that the stereochemistry of the starting material dictates the stereochemistry of the product. If you start with one specific diastereomer, the requirement to rotate the carbon-carbon bond into an anti-coplanar arrangement before elimination will lock the other substituents into place. As a result, one diastereomer might exclusively form a transalkene, while the other diastereomer will exclusively form a cisalkene. The anti-coplanar requirement has massive implications for cyclohexane rings. In a chair conformation, the only way for a hydrogen and a leaving group to be anti-coplanar is if they are both in axial positions on adjacent carbons. This is called a transdioxial arrangement. E2 eliminations in cyclohexane rings can only proceed from this transdioxial geometry. If the leaving group is equatorial, no reaction can occur until the ring undergoes a chair flip to put the leaving group in an axial position. Let's look at bromocyclohexene. If the bromine is in the more stable equatorial position, the adjacent axial hydrogens are not anti-coplanar to it. The molecule must undergo a chair-chair interconversion to place the bromine in the less stable axial position. Once the bromine is axial, the adjacent axial hydrogen is perfectly aligned in a transdioxial arrangement. The base can now attack that specific proton, driving the E2 elimination to form cyclohexene. To summarize eliminations, let's compare E1 and E2. E1 doesn't care about base strength, but it needs a good ionizing solvent to form the carbocation. Its rate depends only on the substrate. It doesn't require special geometry, and because it forms a carbocation, rearrangements are common. E2, on the other hand, requires a strong base. Its rate depends on both substrate and base. It strictly requires coplanar geometry, usually anti-coplanar. And because it is concerted, no carbocations are formed, meaning no rearrangements can occur. Both generally follow Saitseff's rule. Deciding whether a molecule will undergo substitution or elimination can be tricky, but there are guidelines. First, the strength of the reagent matters. Strong bases and nucleophiles push the reaction towards second-order kinetics, SN2 or E2. Second, look at the substrate. Primary halides have very little steric hindrance, so they usually undergo SN2 with good nucleophiles. Tertiary halides are the opposite. They are too crowded for SN2. If you use a strong base, a tertiary halide will undergo E2. If you use a weak base or nucleophile, it will ionize to a carbocation and give a mixture of E1 and SN1. Secondary halides are the hardest to predict because they can react via all four pathways, so you have to look closely at the solvent and the reagent. Temperature is also a great tiebreaker. Because elimination reactions produce more product molecules than they consume, they increase entropy. Therefore, high temperatures strongly favor elimination over substitution. Finally, the specific nature of the reagent helps. Bulky bases like Turk butoxide are too big to act as nucleophiles, so they heavily favor elimination. Conversely, large polarizable ions like bromide or iodide are great nucleophiles, but terrible bases, so they favor substitution. To wrap up our discussion on alkyl halides and their reactions, remember these key points. E1 is a stepwise elimination that goes through a carbocation, while E2 is a concerted elimination driven by a strong base. Both pathways generally follow Zaitseff's rule, favoring the most substituted alkene. However, E2 has strict stereochemical requirements, demanding an anti-coplanar arrangement, which translates to a transdioxial requirement in cyclohexane rings. Finally, always analyze the substrate, the reagent, and the temperature to predict whether substitution or elimination will win out.